Hello everyone, so welcome to our video lecture. In this video today we are going to discuss about SN1 reaction in detail. Okay, so when I say SN1, it is substitution nucleophilic unimolecular. So this is also called as substitution by ionization because first of all ionization occurs and one carbocation is generated as an intermediate, and after that bond combination occurs, right, in between electrophile and carbocation generated and the nucleophile or the reagent we have taken. Okay, also it is known as solvolysis by first order reaction, right? So let us continue with our SN1. See, simply if I say here, then what happens? This water is acting as a solvent as well as reactant as a nucleophile, okay, and the reaction occurs. Here I have used 2 moles H2O, and at the end if I say, then it is H2O and HCl, that is nothing but H3O plus, okay. So let us discuss it in detail. Mechanism. First of all, what happens? This is our reactant or substrate. In first step, first of all, this bond is having high polarity due to this CCl bond having electronegativity difference as well as bond length is high between carbon and Cl. Okay, so first of all this bond breaks. Step 1, heterolysis. It will form this carbocation plus Cl minus. Okay, so dear students, here carbocation is generated. Now what will happen once you get the carbocation? The second step will be attack of nucleophile. Now as this is sp2 hybridized trigonal planar geometry, so attack of this nucleophile occurs from frontal side or back side, means from both sides it is possible. Now what you will get? You will get okay, so this is obtained. Now what will happen? Here in the reaction what I did, I have taken 2 moles of H2O. Now what is the role of second? Now here another mole of water will remove this H plus, so that the desired product will be obtained. Okay, so as is attacks here, you will get the desired product, that is desired product. Okay, so here you can see with this desired product the additional part which you are getting is this Cl minus and this H3O plus. So plus Cl minus plus H3O plus. As I told you earlier, this HCl and H2O is nothing but H3O plus Cl minus. Okay, so as per scientist Hughes, if I say, he explained it in 3-step process such that in first step carbocation is formed as it is, in second step this water attacks, and in third step the extra water, amount of water available as a solvent, that will interact with this. Okay, so it is simply mentioned as step 1, step 2 and step 3. So the first step of SN1 reaction is carbocation generation. Clear to you? Okay, so just note it down. Characteristics of SN1 reaction. Let us understand some characteristics of SN1 reaction. First step is RDS. RDS means rate determining step, or it is also known as rate limiting step. Okay, rate limiting step means that particular reaction step will decide the rate of entire reaction. Okay, based on that particular step only, the rate of all the steps will be determined. Clear? That will be the slowest step of the reaction. Second, first step will be carbocation intermediate formation. Clear? Now, one more important point. Once the carbocation is generated, if rearrangement, ring expansion, I'm not mentioning here about ring contraction because it is a very rare phenomena. Okay, in few cases only it has been observed. So if rearrangement or ring expansion is possible such that, condition applied, such that carbocation becomes more stable, then you have to make that. Okay, if rearrangement ring expansion is possible, then first make most stable form of intermediate and then combination will occur. Now what this meaning of combination? First step is your ionization, carbocation generated, you will make the rearrangement or ring expansion, whatever is possible, make the best or most stable form of carbocation, and then combination means that solvent or whatever you are taking as a other part which will attach with this cation, that combination will occur. Okay. Role of leaving group. Now what is the role of leaving group? Leaving group plays an important role. See, when we say that rate of reaction is equals to rate constant into concentration of substrate raised to the power 1. So rate has nothing to do with, rate is independent of concentration of nucleophile taken in the reaction. Clear? It is independent of concentration of nucleophile. Clear? Now how it occurred? When the reaction was proceeded by taking first case Rx H2O, this is 3 degree, and it was observed, suppose it was observed as X molar, okay, and you get ROH. Now second Rx same H2O, and its molarity was found to be suppose Y molar, let's say, okay, and it was again 3 degree, same, it was found same. So the rate was actually independent of this, the concentration of water here or concentration of water here. It has nothing to do with this thing. Clear to you? Okay. Now, leaving group affects the rate of SN1 reaction as the rate is mainly dependent on the stability of carbocation formed in SN1 reaction. Okay, so here I am mentioning two things. First, leaving group affects the rate of SN1 reaction, and also rate is mainly dependent on the stability of carbocation generated. Now two factors. First thing, because in the reactant itself you are having both the parts. Leaving group is better, then also rate will be better, because if the leaving group is more stable part, is a stable nucleophile, is a weak base, then it will be removed easily and hence the rate will be higher. Or the carbocation generated is very stable, so it will proceed towards forward direction with high rate. Clear? So 2 points: leaving group, better leaving group, or stability of carbocation. Okay. Now next point, when you say rate of 3 degree greater than 2 degree greater than 1 degree greater than CH3 plus carbocation, now this is actually generally, you need to mention generally the rate of 3 degree carbocation will be higher than 2 degree, will be higher than 1 degree, and least for CH3 plus actually it is 0, negligible. Okay, so it is general case. Why I am telling this? Understand, suppose if I say PHCH2Br plus H2O and it gives PHCH2OH plus HBr, this reaction proceeds via SN1 predominantly, and the carbocation generated, as we say this reaction is reversible part, the carbocation generated here is PHCH2 plus. Okay, so this is having 5 resonating structure. Clear to you? So you can understand, if the carbocation generated is very highly stable, although it is primary 1 degree carbocation, but it is having resonance with this phenyl ring, so it is highly stable. So on that basis it is more reactive for SN1. Clear? So remember, this part is generally. Okay, one more case. Allylic and benzylic carbocations have relatively higher rates of SN1. Now understand this thing. When you say allylic and benzylic carbocations, first benzylic, PHCH2 plus, it is benzylic. See, when you say PHCH2Cl, it is benzyl chloride. So this is benzylic carbocation. Okay, if I draw it properly, it forms 5 RS, 5 resonating structures. Okay, and hence this is a very stable carbocation, right? When I say allylic, this is allylic carbocation. Okay, so this is also resonance stabilized. You can see it is having 2 equivalent resonating structure. Okay, so due to these reason and these two are highly stable carbocations and they have relatively higher rates of SN1. Okay, so if I have to conclude about the rate of SN1, then I can say the order will be benzylic carbocation will be higher rate for SN1, then allylic, then you say 3 degree, 2 degree, then 1 degree carbocation. Okay, clear to you? Remember this point. Nature of solvent taken. Okay, now understand one thing. Here I'll be discussing two different points. Okay, let me tell you one reaction simply. CH3 whole thrice carbon having bromine. Okay, H2O, cold water, H2O, warm water. Okay, or simply if I say H2O delta. Clear? So what will happen here? Predominantly the product obtained is alcohol, as we can understand, normal case. Okay, but here what will happen? The predominant major product formed is actually this carbon is having CH3. See, the difference in the two cases is it is your SN1 substitution, but this is elimination occurred. Okay, more properly if I have to say, it is actually dehydrohalogenation occurred. Here dehydrohalogenation, bromine from this carbon and from adjacent methyl hydrogen, so dehydrohalogenation occurred here predominantly. Now why it happened? It happened due to difference in temperature. Okay, why? What happens when the molecule, water molecule, is having high temperature? So the kinetic part is activated, and due to kinetics the rate increases, and hence this elimination occurs. See, here I am not going in detail about this warm water and elimination reaction. We will discuss in our next video lectures. But remember one thing, what we have to do is we have to take solvents with normal temperature. Okay, if you will increase the temperature, then there are possibilities of elimination reaction rather than substitution reaction. Okay, so the water used will be cold water or room temperature, water at room temperature. Clear? Okay, now one more thing here. For same reaction, suppose I say CH3, this carbon is having Cl. Let us take an example, and here I take water 100%, and here I take water plus ethanol. Okay, 50-50% each. Now the rate here is R1, rate here is R2. So dear students, understand the main point here. In this case what will happen? The difference occurs in solvolysis. Okay, here solvent is water, so here occurs hydrolysis. Here I will use the term hydrolysis, here I will use the term solvolysis. Means the interaction of this solvent, water plus ethanol, with this carbocation generated as well as chloride ion formed. Now that interaction releases some amount of energy, and that energy is used for initiation and for the reaction, for occurrence of this SN1 reaction. Remember, okay. See, if I say in general, then what happens? In gas phase SN1, if I say, see, for this reactant in gas phase, simply if you make SN1 reaction, then what will happen? Approx 630 kilojoule per mole activation energy needed for heterolysis. Remember, the first step is slowest step where bond breaking occurs, and definitely bond breaking occurs, it requires the amount of energy. Okay, and that activation energy, bond breaking energy or bond dissociation energy is 630 kilojoule per mole needed for heterolysis. In gas phase I am telling, okay, it is very, very high. Now the difference occurs is in aqueous phase. If I say, if aqueous phase, the same activation energy decreases to heterolysis needs approx 80 kilojoule per mole in somewhere you may find 84 kilojoule per mole as well. Okay, so 80 kilojoule per mole activation energy. Clear? So you can understand the difference. That is why the reaction is generally catalyzed under the presence of solvent. Which solvent is used? Polar protic solvent is used. Okay, the solvent also impacts the rate of reaction. Now what will happen? If there is pure solvent water and if there is ethanol plus water, the rate will vary. The rate will be R1 greater than R2. Why? Because the hydrolysis will be much better in case of water as compared to this ethanol plus water, or if you say simply ethanol. Okay, why? The reason is dielectric constant. Okay, dielectric constant, if I say water higher than formic acid, higher than methanol, and so on. Okay, so what happens? The dielectric, if I say the value, it is approximately 80, it is approximately 59, approximately I am telling, and it is approximately 30 or 33 something, approx value. Okay, these are the approx values. Now water is having the maximum or highest dielectric constant. Now what is dielectric constant? It is simply said as the power to neutralize the charge separation. Okay, you have generated carbocation and Cl minus leaving group. Now this water, polar protic solvent used in SN1 reactions, which is favored by polar protic solvents only. So what will happen? This water will interact with the carbocation as well as with this anion generated, nucleophile generated. Okay, now water has maximum tendency to neutralize these two, means to interact with these two, as compared with formic acid, as compared with ethanol or methanol, whatever be the case. Okay, so among all the polar protic solvents, water behaves as the best solvent used, and it will have the maximum rate or highest rate. Clear to you? I think you have understand the role of solvent. Okay, now here you can write one more point. Polar protic solvent favors SN1. Stereochemistry of SN1 reaction. So dear students, this is one of the most important part of SN1 reaction. Understand it very carefully. When you say stereochemistry, you can simply recall it's about stereoisomerism part. It's about orientation of atoms or molecules in space. Okay, so let me first of all give you one basic example. R1, R2, R3, and this is halogen. You take water. Here you get two products. What product? R1, R3 as it is, R2 here, OH here, plus R1, R3, R2 comes this side and OH this side. Okay, the two products generated. Why two products? Because optically active reactant having chiral center. Okay, now why I needed to write optically active reactant having chiral center? Because as you know, the optically active compound does not mean that it will be having always chiral center. You remember, right? So here in the reaction you generate carbocation first of all. Okay, this carbon having R1, R2, R3 and plus charge, right? Now what is possibility? Water may attack, water can attack from this side. Okay, when I say this side, it is back attack. Back attack why? With respect to this leaving group. And from this side, this is called frontal attack. So frontal attack will give you retention product. You can see here, this is your retention product. Okay, from same side means retention, and from back side it will be inversion product. Okay, clear to you? So carbocation generates and then attack can occur from both the sides, frontal or back side, back attack, and hence the products are both retention as well as inversion. Okay, here comes the main question, sir. What will be the composition of this? Whether the product obtained is optically active or inactive? Because as you see in these two, I can say that one will be D configuration and the other one L configuration. Okay, so if one is having D configuration, one will be having L configuration. So definitely if it rotates PPL in clockwise, it will rotate in anti-clockwise or vice versa. Then the question arises, if this is 50% and this is also 50%, the mixture will be racemic mixture, or you can say racemic modification or perfect racemization occurs in the reaction. Clear to you? So if perfect racemization occurs, then the product will be optically inactive. Clear? So now the question is, how much percentage of retention and inversion will occur in the reaction? So first thing is clear that in SN1 reaction, the product generated will be retention as well as inversion. Why? Because attack can occur from back side as well as front side. Clear to you? So first thing is clear, retention, inversion. Now let us understand how much amount of retention and inversion product will be formed in the reaction. Percentage racemization in SN1. Percentage racemization in SN1. Generally 100% racemic mixture is formed. Generally I am telling, okay, not always. 100% racemic mixture is formed in SN1 reaction. That is perfect racemization, or you call it as racemic modification. Same thing. Okay. What does it mean? It means 50% D plus 50% L means, or 50% retention plus 50% inversion. Okay, so you can understand generally racemization occurs 100%, 50% D, 50% L, or 50% R, 15% S. So 50% retention, 50% inversion. Now let me first tell you in what cases or how the percentage of retention and inversion can vary. First of all, understand that thing. "100% racemization in SN1 is not true always." Now first of all, understand the reason behind this. Okay, suppose you are having Rx, this is having delta positive charge, this is having delta negative charge, and this is having polarity, polar bond covalent. Okay, polar covalent bond, it is your substrate. What will happen? R plus X minus, initially this bond will be broken. Okay, in SN1 reaction carbocation is generated, so this is your, this part is R plus and X minus. Okay, this is called as intimate ion pair. See, what I mean to say is, when this bond is broken, but it is broken in by heterolysis. Okay, so the charge separation is plus and minus. So due to heterolysis, they are having strong electrostatic force of attraction right now. They are not separated far away. Okay, here just is heterolysis is occurred. That's it. Now what will happen? R plus X minus. Here I mean to say solvent separated ion pair. Okay. Now this R plus and X minus is generated. That's why here we use what? Polar protic solvent. Now polar protic solvent has a tendency to interact with R plus and X minus. So it will separate R plus and X minus. And finally we have R plus and X minus. Okay. This is your leaving group and this is your carbocation. Now here you are having carbocation and leaving group is far away. Okay. Now understand. When will the reaction start? Reaction starts once the heterolysis is done. Reaction starts just after heterolysis. Now what I mean when I say reaction starts just after heterolysis, reaction is heterolysis or also reaction part only. Okay, so once the heterolysis is done means this will be generated. Now from this part up to this part, the attack of the nucleophile or the reagent you have taken, suppose I am telling water, then water can attack at this part or this part, means attack can occur in all three cases. Hence the deviation in percentage of retention and inversion occurs. Now understand how. Suppose you are telling attack occurs here. If water attacks when this you are having intimate ion pair, means they are attracted by electrostatic force of attraction. In this case what will happen? Attack cannot occur from this side. Okay, attack will occur from this side only. Why? Because attacking reagent is also, or your nucleophile attacking is nucleophilic, same charges, so they will repel each other. So attack cannot occur at all from this side, attack will occur from this side only. Clear to you? And hence you can understand the major part in this transition state will be SN2 type, and hence inversion product will be a bit major. Now let's see this side. So it cannot attack from this side, it will be hindered. Attack can occur from this side mainly. Okay, mainly from this side. Now here you can understand, as they are far away, they are far away from each other. Now attack can occur from this side or this side. This is also true, this is also true. And hence if attack is occurring, which generally happens in SN1 reaction in this way, and hence we say racemization or racemic mixture is obtained. But as I told you, in many reactions you will observe that there is no perfect racemization. There will be, in some cases you may find that there is approximately 49 plus 49, approximately 98% racemization and 2% extra inversion. Due to what factor? Due to these two parts. Attack is occurring and transition state is having little bit more towards attack from backside style. Okay, so note it down properly first. So dear students, here I have taken a single reactant. All these cases are SN1. This reactant will mainly go forward with these nucleophiles via SN1. Why? Because it can form very stable carbocation, although it is 1 degree carbocation. Okay. Now this carbocation is generated. Now when the nucleophile is water, it will form PHCH2OH. Here the solvent or nucleophile is water, so the reaction is called as hydrolysis. Okay. Now second case. When I say second case, here methanol, so it will be PHCH2 OMe. Now this is solvolysis, but here we say specifically methanolysis, because here you have taken methanol, so it is methanolysis. Okay. Now next, when you take ETOH, it will form PHCH2OET. So this is simply called ethanolysis. Okay, because you have taken ethanol, so ethanolysis. Ethanol is making this substitution reaction. Clear? Next, when you take HCOH, it is formic acid. So you form PHCH2OCOH. So this is simply called formolysis. Clear? And last case, when you take CH3COH, then it will form PHCH2OCOCH3. Now this is called, it is acetic acid, so you will call it acetolysis. Okay. So dear students, here you can understand from these all cases that with respect to these solvents with the same reactant, the names are different. Hydrolysis, for this solvolysis it is methanolysis, ethanolysis, formolysis or acetolysis. Clear to you? Note it down. So these are some special cases I have discussed you. Okay. Compare rate of SN1 reaction in given species. Okay, compare the rate of SN1 reaction in given species. First, so in the given cases, you just have to compare rate of SN1. Okay, do it by yourself first. Okay, so let us understand. This is OTS. If you remember last lecture of living groups, you remember tosylate ion. It will be removed as O minus TS. Okay, so this carbocation generated. Here also 2 degree carbocation generated with Br minus. Now, if simply I have to say in these two cases, rate of SN1, what I will say is rate of SN1 will be higher in first. So A greater than B, because it is super living group. If you remember OTS, tosylate ion. Now CH2Br, CH2Br. See, here what I did, living group is same, but carbocation is different. It will form CPM carbocation, and this is primary carbocation. See, after rearrangement, definitely it will form CPM carbocation, but before it will be 1 degree carbocation, that is not stable. Okay, so it will be not having more rate of SN1. So you can say A greater than B. So in earlier case, it was about living group. Here it is about carbocation generated. Now check this one. See, if this iodine minus is liberated, then you will get this plus charge. And if you remember, this forms 7 equivalent RS. Okay, this plus charge will be having delocalization over entire ring with 6 pi electron. It is cyclic and all atoms will be planar in the carbocation generated. Now this one, this I minus is liberated, plus charge, resonance this side as well as this side, but non-aromatic. Okay. Now this one, if I minus is liberated, it will be having complete resonance in entire ring with 4 pi electron, cyclic, planar, but 4 pi electrons, so it is anti-aromatic. So this will form anti-aromatic carbocation, this will form non-aromatic carbocation, and this will form aromatic carbocation. So simply you can understand among the carbocation generated stability is aromatic, then non-aromatic, then anti-aromatic. So the order will be A, B, C. If I say this one A, this one B, and this one C. Clear to you? Okay. Okay, so in these three cases you have to compare the rate of SN1. Let us understand. Here if Cl minus is liberated, this will be 2 degree carbocation. Along with that, it is having from this side 2 alpha H. Here you cannot say that this H will cooperate this one, because if this hyperconjugation occurs, suppose in the carbocation generated, then it will make here pi bond, which will be highly unstable due to bridgehead position according to Brett's rule. Okay, so this 2 alpha H is cooperative for this carbocation generated. But here if you say this Cl minus generated minus Cl minus, it will cause plus charge. Brett's rule violated. Ring size less than 8 carbon atom. Okay, you can see it here. The ring size is even less than 8 carbon atom. So this plus charge in the bridgehead carbon atom is highly unstable. Why? Because as per plus charge, it is sp2 hybridized carbon, and sp2 hybridized carbon atom must be trigonal planar. Here you can see if it becomes trigonal planar, this side and this side, see, it is not trigonal planar, so it is having high angle strain, so it is highly unstable. So in these two, if I say, this will be having higher rate of SN1. Here if you see this is benzyl chloride, 5 RS, good. Here it is having 2 benzene rings, so this carbocation will be having more resonance, so the rate will be higher for this. If I compare this one, see, it is having 3 benzene rings. Also one more factor is, it is highly steric crowded compound. Steric hindrance is very, very high here. Why? Because this Cl, pH, all 4 bulky groups. So once Cl is removed, the strain in the compound will be decreased. Okay, so it is having very, very high rate of SN1 reaction. Clear? Now check this one. Suppose here Cl minus liberated, plus charge having 4 alpha H. Here Cl minus liberated, it is having this oxygen lone pair will be inside the ring, so it will make aromatic compound, aromatic. Okay, now this one, this Cl is minus is liberated, it is having resonance. So as you know, aromaticity factor is dominating, so you can say B more than resonance and alpha H, so C then A, so the order will be B, C, A. Clear? Okay. Okay, now in these 4 cases, you have to find the order of rate of SN1. Okay, see, the common factors, never consider the common factors. Here also, this will be plus charge, this will be plus charge, same. In all the cases, carbocation part in upper side is same. Okay, now leaving group is same. So consider the variables. Here it is CH3, which has plus H effect and plus I effect on this ring. This is having OCH3, which is having plus M effect on this ring. It is having minus M effect on this ring, and it is having no plus H or no plus I or no plus M, 0 effect. Okay, so with respect to these, now what will happen? I am just giving you one example. Okay, now this will cause resonance. If I make extended resonance, then what you will get? Double bond here, double bond here, this plus charge, and this is your group. Okay, now due to carbon generation and resonance, double single plus charge conjugation, and then again double single double extended I have made. So plus charge will come here. Okay, from this point plus charge will come to ortho, then plus charge will come to para. Then when plus charge is here and here you are having different groups. Now understand, this plus H group will be stabilizing this cation, plus M will also stabilize, and it will stabilize to more extent, minus M will make unstable, and this is normal. So I can say rate of reaction among these cases will be, suppose this is A, B, C and D, then I can say the order of rate of SN1 in this, maximum will be B, then A, then D and then C. Okay, because this NO2 will make it unstable. Clear to you? Okay. Okay, here I have taken 3 cases. Understand one by one. In first case, F minus is a leaving group. As we know, it is having 2p overlapping. Also, fluorine is most electronegative. Also, F minus is poor leaving group. Okay, so all these 3 factors. So here I can say no SN1 reaction. Okay, next, one more factor here is if F minus is liberated, you will get CH3 plus carbocation, which is unstable. Here all rest factors are side, but here CH3 plus is generated. CH3 plus unstable carbocation. So for this reason I can say here no SN1. Okay, now check third one. In third one, this carbon is having, see, carbonyl carbon atom is having always delta positive charge. Okay, now this I minus is liberated. What you will get? You will get PHC double bond O CH2 plus. Now this is having delta plus, and in front of plus charge you are having again plus charge. It is just like beggar in front of a beggar. Okay, both are begging with each other. So it is this plus charge and this plus charge, highly unstable carbocation. Highly unstable carbocation. So no SN1. No SN1 in this case also. Okay. This is haloarine PHX. Okay, or you can say aryl halide. Now this is your vinyl chloride. Okay, ethynyl chloride. The 2 cases, if I say, in both the cases they are in conjugation resonance. Okay, so in both the cases there will be no SN1. Reason, here the carbocation generated will be highly unstable because the carbon having pi bond will be having plus charge. Here also if Cl minus is liberated, plus charge will come in this carbon which is having pi bond. So in both the cases carbocation is highly unstable. One thing, another thing is both are conjugated system. So in those cases SN1 is not favorable. Remember this thing. Also I told in case of CH3F, also I told in case of bridged carbon atoms, no SN1 is favorable. Okay. So dear students, here we discussed about different factors about SN1 reaction, characteristics, and how SN1 reaction occurs, about the stereochemistry. Retention as well as inversion will occur, but we cannot say that perfect racemization will occur, okay? Because as I told you, once the heterolysis is done, nucleophile can attack any time after heterolysis, and hence the reaction can have perfect racemization or it can have major portion of inversion than retention, okay? So we'll continue in our next lecture.